Chapter 7 is Analytic Trigonometry. So this is a chapter where we kind of put to use all the identities, or all the relationships, I should say, that we learned in Chapter 6. To kind of give you a rundown of the chapter, in natural sciences and engineering, complicated trig expressions need to be simplified. So in section 7.1, we're verifying identities. We're kind of playing with identities, and we're going to try to get one of the sides of the identity equal to the other side. So we're only allowed to play on one side and trying to get it to equal the other side. In section 2, we're going to solve equations involving trig functions. In 7.3, 7.4, and 7.5, a lot of useful formulas are derived. So there's going to be some formulas, difference formulas, multiples, and then we're going to apply those to some applications. And then finally in section 7.6, we talk about inverse trig functions. So section 7.1, we're verifying trigonometric identities. We're going to be doing this throughout the chapter, but to begin with, we are starting with, you need to be familiar with these basic fundamental identities. These are some identities that you probably should, or at some point will, have memorized. So first of all, we have the reciprocal identities. Cosecant is the reciprocal of sine, or 1 over sine. Secant and cotangent are also reciprocals. The tangent and cotangent identities, sine over cosine, and cosine over sine, and then the Pythagorean identities. And really for the Pythagorean identities, the only one that you really need to remember is the sine squared plus cosine squared equals 1. We get the other two, the top one, if we divide everything by the cosine in that first equation, then that's how we get sine over cosine squared plus cosine over cosine squared equals 1 over cosine squared. That's how we get the tangent squared plus 1 equals secant squared. And similarly, if we were to divide everything by sine, we would get the bottom Pythagorean identities. So to begin with, we're going to verify a few identities. And again, the big thing to remember on these is that you can only do something to one side. So that whole idea of property of equality, where if you do something to one side, you have to do it to the other side, we're not going to do any of that, because we're only allowed to work on one side of the equation or identity at a time. And there's no magic way to all of a sudden look at these and say, oh, I know how to do these. When I was first learning these, it takes a lot of trial and error. It's a lot of, you try something, hey, I'm getting somewhere, so you keep going, or I've run into a roadblock and I can't go any farther. So one of the first things that I try to tell students is a lot of times, not always, but a lot of times it's easier if you can get things all in terms of sine and cosine. So the first thing I'd like you to do is change that equation number 1. Again, only mess with one side, and I'd like you to work on the left side. Change everything into sine or cosine. Well, secant is 1 over the cosine, so now I have the left-hand side and nothing but cosine. And if you notice on the left-hand side, I have them being subtracted, and on the right-hand side, I have them being multiplied. So somehow I need to get rid of that subtraction, maybe somehow get it in terms of one fraction. So if I were to think about getting a common denominator, if I were to multiply this cosine by cosine theta over cosine theta, then I have 1 over cosine theta minus cosine squared theta over cosine theta. Now I have a common denominator. So I can write my whole numerator over my common denominator. Now I have a cosine squared, so whenever I have a cosine squared, especially if there's a 1 involved, I'm going to think about this Pythagorean identity up here. And so if you think about this Pythagorean identity, I have this 1. If I were to subtract cosine from both sides, I would have 1 minus the cosine squared equals the sine squared. So I can change my numerator on this one to the sine squared of alpha over the cosine of alpha. Now I'm super close to what I need it to be. Sine squared, I'm going to rewrite as sine of alpha times the sine of alpha. And then all of this is over cosine. Or I could just write this one over the cosine of alpha, right? I can extend that, or I can just write that over. So now I have the sine of alpha times sine over cosine is the tangent of alpha. And that's what I needed. So I have verified that identity. I've made the left-hand side equal to the right-hand side. When we take a look at number 2, it'll be a whole lot easier to simplify the right-hand side, try to somehow combine all this and get it into the secant of beta, rather than figure out how to expand the secant of beta. So again, the first thing I'd like you to do is leave the left-hand side alone. Go ahead and change the right-hand side into everything in terms of sine and cosine. So tangent is sine over cosine, cotangent is cosine over sine. Now again, I've got to get rid of this addition, because I have two terms here, and I need to get it down to one term. So I'm going to distribute, and when I distribute to the first term, I get the sine squared of beta over the cosine of beta, plus, and when I distribute it to the second term, the sine on the numerator cancels with the sine on the denominator, so I'm left with just the cosine of beta. Now, this is similar to what I had up above. I have a denominator on this one, and I don't have a denominator on that one. So I'm going to get a common denominator. I'm going to multiply the second term by 1, cosine of beta over cosine of beta. And so then I'm going to end up with sine squared of beta over cosine of beta plus cosine of beta over cosine of beta. Getting really close to, cosine squared of beta over cosine of beta. Now again, I'm going to come on up here. I have a common denominator, so I'm going to write sine squared of beta plus the cosine of beta over the cosine of beta. I forgot my squared again. Again, I have a sine squared, cosine squared, so if we go up there, we remember that sine squared plus cosine squared is 1. It's still over the cosine of beta. And then I'm going to remember my reciprocal identity, and 1 over the cosine is the secant of beta. And again, that's what I was supposed to get. Number 3, I have a fraction equal to a fraction. And it is oh so tempting to solve this the same way you would solve a proportion by doing cross multiplying. But remember, we can only work on one side at a time. So I'm going to take this first one, and maybe if you notice, I would hope your algebra is fresh enough in your mind to recognize that if I take 1 minus the sine of alpha times 1 plus the sine of alpha, that's a difference of perfect squares. So again, I can't cross multiply, but what I can do is I can multiply this fraction on the left-hand side by 1 plus the sine of alpha on the top and bottom. And by doing that, I'm simply multiplying by 1. So the left-hand side of my equation is going to become 1 plus the sine of alpha times the cosine of alpha over 1 plus sine of alpha and times 1 minus the sine of alpha is 1 minus the sine of alpha squared. If you want to confirm that, then I would go ahead and FOIL that together, but that's what you would get. So now, 1 minus the sine squared of alpha, if we remember from the other side, so my numerator is going to stay the same. But if you remember your Pythagorean identity, 1 minus the sine of alpha, I could derive that very easily from the Pythagorean identity, and that's equal to the cosine squared of beta. Now I can see that I have this cosine on the numerator, and I have a cosine squared on the denominator. So the cosine on the numerator can cancel with one of those. And I'm going to have 1 plus the sine of alpha over the cosine. Whoops, somehow I changed my alphas and my betas. That should be an alpha. 1 plus the sine of alpha over the cosine of alpha. And again, that's what I needed to get. Oftentimes there is more than one way to attack these identities to verify them. Sometimes, like some of the previous examples, it's obvious which side to start with because there's more going on. You're trying to simplify it to one trig function. In this case, the first thing I want to do is I'm going to get rid of that squared. So I'm going to multiply those out. Remember, you can't just distribute that squared. So I would like you to pause the video and multiply this out. And then while you're at it, go ahead and change everything into sine and cosine after you multiply it out. So first of all, when I multiply it out, I get that. And now I'm going to change everything into sine and cosine. And now if you notice, I have 3 terms, and the denominator of that term is cosine squared. When I multiply those two fractions together, the denominator would be cosine squared, and that denominator is cosine squared. So now let's go ahead and write this as one fraction over a denominator of cosine squared. Now I'm hoping you recognize that you can factor the numerator, and your denominator you can rewrite using a Pythagorean identity. So my numerator is, I can factor as the sine of theta minus 1 and the sine of theta minus 1. Again, perhaps you can see this as x squared minus 2x plus 1, and so this is how that will factor. Using the Pythagorean identity, I can write the cosine as 1 minus the sine squared of theta. Again, hopefully you can recognize that this is a difference of perfect squares, so I can write this as 1 plus the sine of theta and 1 minus the sine of theta. Now I have the sine of theta minus 1, but I have 1 minus the sine of theta. So I'm going to factor a negative 1 out of this. That's going to give me 1 minus the sine of theta times the sine of theta minus 1. So now you can hopefully see that I can cancel out my 1 minus the sine of theta. And then I'm just going to distribute that one, this negative 1, back into this one. So that's going to give me a positive 1 minus the sine of theta over 1 plus the sine of theta. And again, that's what I needed to end up with. And number 5, trig substitutions are sometimes used in calc. So let's talk about one of these. So we want to take this expression and express it in terms of a trig function without any radical. So we're going to let x equal a times the sine of theta. So we're going to just do some straight up substitution here. And I have a squared minus a sine of theta. And all of that is squared because my x is squared. This is going to be a squared minus a squared sine squared of theta. Just squaring everything on the inside. Now if you notice with what's on the inside, I can factor out an a squared, and I'm left with 1 minus the sine squared of theta. Again, if we remember our Pythagorean identity, 1 minus the sine squared of theta is the cosine squared of theta. Now I have two things being multiplied together, so I can take the square root of both of those, and that's going to be a cosine of theta. And normally, when you take something out of the square root, you would need absolute value bars around it. We don't need absolute value bars around it in this case, because it's given that a is greater than 0, and if theta has to be between negative pi over 2 and positive pi over 2, then cosine will also be positive. So there we've just transformed that radical of a squared minus x squared into a trig function with no radicals. These can be very tricky problems to do. They take a lot of trial and error. They take just a lot of practice. So please don't be discouraged, and please come to class and we can go over some more.